Hello everyone and welcome to my YouTube channel The Physicist. So today we delve into the fascinating realm of crystal structure. Okay, so today we will start our unit first called crystal structure. So in today's video we will discuss crystalline and amorphous solids. Okay, so today we will discuss crystalline and amorphous solids. Amorphous solids. We will start by defining these concepts, followed by in-depth exploration of their characteristics. Okay, we will discuss their characteristics, properties, differences, and the real world examples. So we will discuss characteristics, properties, differences, and real world examples. Okay, so let's embark on this enlightening journey into the world of solid materials. Okay, so as we know that the matter of the universe can be divided mainly in three forms. Okay, well, if we talk about on earth, okay, there are other states of matter which are mainly on stars, for example plasma state of matter, but for the matter of the subject we will discuss only three. Okay, so we know that first phase is, or first type of matter is gas. Okay, in which the molecules are very far apart from each other. Okay, in gases the molecules, like example is air. Okay, example is air. So molecules of the air are very far apart, so that there is less force of attraction between the molecules, so they wander about in the space. Okay, they are moving, some are moving here, some are moving there, some are moving in this direction, so they are randomly moving in different directions. So when we go from gases to liquids, okay, the liquids, which is the second form of matter. Okay, in liquids these molecules comes closer, so that they have a measurable attractive force between each other. Okay, so the molecules of water are very near to each other, like this. Okay, okay, this is only a representation. In actuality they are much closer than that. Okay, so liquids, so in liquids these molecules are also moving around. For example, if we consider these two molecules, this is a molecule A and this is a molecule B, so now they are very close to each other. But if we look at water, after some time they may be very far apart. So in water also the molecules are constantly moving about with respect to each other. Okay, so this is A and this is B, so they are at a larger distance than they was previously. Okay, so we see that in gases and in liquids the atoms or molecules of these matter move around, okay, freely. Okay, in liquids there are more stronger force than in case of gas. That's why the liquids have some volume. Okay, but the gases, they have no volume, no shape. Okay, so they will take the shape of container. So if you put a gas into a box, it will take a shape of box. Okay, if you contain gas in a balloon, it will take shape of a spheroid. Okay, so they don't have volume. For example, if you put a gas in small box, then it will cover small box. But if you empty this small box into a large box, then the gas will take the shape of the large box. It's not a definite shape, but it will be found in full volume of the large box. Okay, so the gas that was previously in small volume is now contained in large volume, so there is no definite volume of a gas. Okay, and liquids on the other hand have they have volume because of the more attractive forces than the gases. They remain with each other. The molecules of the liquids remain with each other closely. Okay, so they have a definite volume. So definite volume. Okay, but they do not have not definite shape. Okay, if you pour milk into a glass, it will take the form of glass. Okay, so take the form of container. Okay, or if you pour the liquid into something else, it will take the shape of this. So not definite shape. Okay, so these are liquids. But when the atoms of matter are not moving around very much, they got stuck together and arrange themselves in a configuration with as low energy as possible. Okay, so when the atoms are not moving around, they settle together. Okay, they stuck together, they are not moving about each other. Okay, they stuck at positions. Okay, so they don't move about their position, but they can only vibrate. They can only vibrate about their mean position. Okay, so the atoms will form a repetitive pattern. They will arrange themselves in a repetitive pattern, and for these reasons we have solid materials. Okay, so in solids we have, due to the forces of attractions are greater than liquids. Okay, and gases also, and so that we get a solid material. Okay, so they will have definite shape. As you can see, bricks have the definite shapes. Okay, they do not change shape if you keep them in different containers. Okay, so definite shape and definite volume. So this is a property of solids. Okay, so we get repetitive patterns in of the atoms in solids. Okay, this repetitive pattern of atoms is called a crystal. A crystal. Okay, so we will discuss in detail what a crystal is later, but we can say that it is composed, a crystal is a solid that is composed of atoms and other microscopic particles. Okay, so crystal is made up of atoms or molecules. Okay, so or molecules that are arranged orderly. Okay, that are arranged orderly. So there is a order in the arrangement of these atoms or microscopic particles, and this type of solid is called a crystal. Okay, and by orderly we mean that they arranges themselves into a repetitive array, rapid, like this. Okay, this pattern repeats in whole directions. So here we are showing in 2 dimensions, but you can imagine that pattern is um, repeating itself into 3D. Okay, so they arrange in an orderly repetitive array. Okay, repetitive array. Okay, so this is the shortest definition of crystal. Okay, it may not be complete definition, but yet it is true description of a crystal. Okay, we will discuss in detail later, obviously. Okay, so there are 3 general types of solids. Okay, so let us do classification of solids. Okay, so in general there are 3 types. Okay, there are 3 types. Just write them down. So first type is called amorphous solids. And the second type is called polycrystalline solids. Okay, and the last is single crystal solids. Okay, single crystal solids. So matter or the solids, the solid can be classified into 3 types based upon the intermolecular forces that bind the large number of atoms into a form which has the volume and definite shape of its own. Okay, so these are amorphous solids, polycrystalline solids, and single crystal or single crystalline solids. Okay, we will discuss amorphous and single crystal solids in details, but we will just give a brief definition of polycrystalline solids. Okay, so these the solids are categorized into these 3 categories based upon the size of order regions. Okay, so this classification is based on the ordered region within the material. Okay, based on the ordered region within the material, ordered region within the material. Okay, so this classification is based upon the ordered region within the material. We will see that amorphous have short range order, and they will have long range order. Okay, it means that if you go long distances into a single crystal, you will have the same pattern repeating. But in amorphous solids, they are short range. There is a short range order. It means that the order is repeated only up to few molecular distances. Okay, not in whole of the solid. Okay, so in different parts of the solids we will see different arrangements of atoms. Okay, and in polycrystalline material the solid is made up of grains which are highly ordered crystalline regions of irregular sizes and orientations. Okay, so if we consider a solid like this, there will be some regions of unequal sizes. Okay, there are some regions of unequal sizes. These regions are called grains. These regions are called grains. Okay, and these grains are highly ordered crystalline regions. Okay, for example, if we see this region of space, it is highly ordered. Also this region of space will be highly ordered, and also this region of space will be highly ordered, like this. These all regions of spaces will be highly ordered regions of spaces. Okay, but as you can see from these, the size of these grains are irregular. It means that some are big and some are small, and the orientation is also different in different regions. Okay, and this type of material or the solid is called polycrystalline solid. Okay, polycrystalline solid, it means it contains polycrystals, that is more than one crystal structure is present in these type of solids. Okay, that's why it is called polycrystalline solids. So now question arises, why we have to know these different types of materials. Okay, what if we do not bother about if this is amorphous solid, this is crystalline solid, and this is polycrystalline solid? Okay, so what is the reason behind that we should know what type of solid is that? Okay, so let's discuss this question. So many important properties of the material are found to depend upon the structure of a crystal and on the electron states within the crystal. Okay, so there is a correlation between the properties of solids, like mechanical properties, electrical properties, structural properties. Okay, so the properties of solids are related with the structure of crystal. Okay, structure of crystals. Okay, so if the material is crystalline, it can be a better conductor. Okay, if it is not a for example, if it is an amorphous solid, it may not have a good mechanical strength. Okay, it cannot be used in structures, for example. Okay, so that's why these classifications are very important, and we should know about the solid which is amorphous solid or which is crystalline solid. Okay, the study of crystal physics aims to interpret the macroscopic properties, like this: mechanical property, electrical property, structural property, or thermal property, in terms of properties of microscopic particles. Particles microscopic particles like atoms or molecules, of which the the crystal is made up of. Okay, so these properties, these are the macroscopic properties. Okay, macroscopic properties, and these can be explained by understanding the microscopic particles, that is the atoms or molecules of which the solid is made up of. Okay, so now let us give definitions of amorphous and crystalline solids. Okay, so first we will define the amorphous solids. Okay, so what are amorphous solids. First of all, if we look at the word amorphous, it means that without form. Without form. Okay, so the word amorphous mean without any form. Okay, therefore the amorphous solids are those solids which lack the regular arrangement of atoms or molecule, and hence a short range order in their structure. Okay, those solids which lack the regular arrangement. So those solids which lack the regular arrangement of atoms or molecules, and hence a short range order in their structure. So amorphous solids have no regular arrangement of atoms or molecules in their structure. So if we consider this as the solid, so the atoms or molecules, if this is an amorphous solids, are arranged in totally random way into this solid. Okay, so like this. Okay, so atoms and molecules will be randomly arranged. Okay, like this. So these are, each dot is representing a atom or a molecule of the solid, of the amorphous solid. So this is amorphous solid. Okay, amorphous solid. Okay, you can see from here there is no regular arrangement of atoms are randomly distributed across the solid. Okay, so this type of solid is amorphous solids. Additionally, you can see that there are different separations between atoms or molecules. Okay, each in all different points the atoms are differently separated. Okay, so all the atoms are differently separated. Okay, differently separated. Also the orientation, look at the orientation here. The orientation of this bond is that way, here the orientation is that way. Okay, so they have different orientations. Okay, so atoms or molecules of amorphous solids, they are differently separated, randomly arranged, and are in different orientations. So we can say that there is a total randomness. So there is total randomness into the amorphous solids. Okay, so this randomness is in all direction wherever we go. If we go to this direction, we find randomness. In this direction there is randomness, in this direction there is randomness, in this direction there is randomness, and also in this direction. So in 3D, wherever you go in an amorphous solid, you will find randomness into, okay, randomness into these types of solids. Okay, the amorphous solids may be regarded as super cool liquids. Okay, they may be regarded as super cooled liquids. Okay, super cool liquids. So they are just like liquids but super cool liquids. Okay, they have very small structural unit with a short range order. Okay, but unlike liquid, they have stiffness. They have stiffness. Okay, so they are hard as compared to liquids. Stiffness and rigidity is also present in these type of solids. Okay, so opposite to this can be regarded as super cooled liquid, but opposite to liquid, they have liquids, they have stiffness and rigidity due to their highly enhanced viscosity. So these properties are due to their highly enhanced viscosity, highly enhanced viscosity. Okay, highly enhanced viscosity. Highly enhanced viscosity is the reason for behind their stiffness and rigidity. Okay, so that's why such solid remain fixed in their position while they are free to roam all the volume of liquids. Okay, so that's why the atoms in a super cool liquids, or also called amorphous solids, remain at their fixed positions. Okay, due to the highly enhanced viscosity of these materials. On the other hand, if we talk about, for example, crystalline solids, crystalline, if we talk about crystalline solids. So crystalline solids can be defined as those solids which contain regular repeated pattern of atoms or molecule, and hence a long range order in their structure. So those solids which contain the regular repeated pattern of atoms or molecules, atoms or pattern of atoms or molecules, and hence a long range order. Okay, so there is a long range order in their structures. Okay, so these type of solids are called crystalline solids. Okay, so there is a regular arrangement of atoms. Okay, they follow a particular geometric arrangement. Okay, these atoms are arranged in particular geometric shapes. Okay, so these regular arrangements are in particular geometric shapes. For example, in 2D, if we consider a square crystal. Okay, so we can make a square crystal by this, like this. Okay, so this is a square crystal in 2 dimensions. Okay, so every intersection of these lines is an atom. Okay, there is an atom or a molecule that is present there. So this is a crystal. So we can see that in crystals there is such type of orderly arrangement. Okay, these atoms are arranged into a geometric shape, into a particular geometric case, with geometric arrangement, which is in this case a square. Okay, so this crystal is following the square pattern. Okay, square pattern. So there is the regular arrangement of atoms. Okay, every atom we know will be found at same distance, for example A. Okay, also in this direction the distance will be A in a square lattice. Other type of lattices are crystals are also possible. Okay, For example, a rectangular crystal, okay, in which case these lengths will be different, okay, instead of a it will be of different length b, okay. So they follow a particular geometry, okay. Some common examples of crystalline solids are rock salt, okay, rock salt, or the common salt, okay, NaCl, which we use in our houses, calcite, sugar. These are crystalline solids. Quartz, okay, these are the crystalline solids, okay. And there is a single crystal, okay, in which there is a regular periodic arrangement of atoms like this, okay, regular periodic arrangement of atoms or molecule in 3 dimension throughout their volumes, okay. Okay, so these are crystalline and amorphous solids, okay. So we saw that there is a randomness in all directions wherever we go in an amorphous solids. So we can say that the behavior on average is same everywhere, okay. If you go in this direction there will be randomness, if you go in this direction there will be a randomness, if you go in this direction there will be a randomness. So on average we can say that the behavior is so behavior is same in all direction, direction in all directions the behavior is same, okay. So the randomness is in all direction, so we can say that they have isotropic nature, nature, okay. It means that all the properties will be same in all directions, okay. All the properties will be same in all directions. So this type of properties are called isotropic properties, okay. Whereas in crystalline solids we can have different bond length in different directions, okay. For example, if we go in this 2D crystal, if this is a rectangular crystal horizontally, then we will find a distance a, that is bond length is a between the crystals, okay, between the atoms, okay. But in here in these directions the bond length may be different. Due to this there will be different properties in different directions. So different properties in different directions, okay. So this type of, so we can say that due to different properties in different directions we can say that the crystalline solid shows anisotropic nature, okay. That is having different properties in different direction, whereas the amorphous solids show isotropic nature, okay. It means that they have basically on the average same behavior in all direction. So they will conduct same electricity in this direction and also in this direction if they are conductor, okay. They will conduct same amount of heat in this direction and same amount of heat in other direction. So these show isotropic nature. Okay, on the other hand, the crystalline solids shows anisotropic nature, so they will show different properties in different directions. Okay, for example, this bond length. Okay, bond length. So here the bond length is A in this horizontal direction, but the bond length is B in this vertical direction. Okay, so different properties in different direction, hence called the having anisotropic nature. Okay, so if you look into different directions, they will show different properties. For example, in this direction the current conduction will be different than in this direction, which will also be different in, for example, this direction. Okay, so that's why they are said to have possessed the anisotropic nature. Okay, so in a crystalline solid, we will have fixed bond length. Okay, fixed bond length. Okay, however, there are different bond lengths in different directions, but they are fixed. Okay, if we go in this direction, all the bond lengths are A, and if we go in this direction, all the bond lengths are B, but the bond length is fixed. Okay, so that's why the crystalline solids have sharp melting point. Sharp melting points. Okay, so all the crystalline solids melt at same temperature, which is characteristic of that material. Okay, so the full solid will melt at same temperature, same melting point. Okay, so the full solid, due to the fixed bond length, okay, all the bonds will rupture at the same temperature, so that's why the melting point of the crystalline solids are fixed and they have sharp melting points. Okay, on the other hand, because in full amorphous solids we will have different bond lengths in different direction. For example, there the bond length is different, there the bond length is different, there the bond length is different, so different directions will have different bond lengths and they will break at different temperatures. Okay, so if the bond is shorter, for example this bond, it will break at early temperature, because when we heat a solid the temperature goes up gradually. Okay, first it will go to, for example, if it is at 0 degree, then it will first go to 1 degree, then 2 degree, then 3 degree, so it grows or increases gradually. Okay, so smallest bond will break first, then the longer and then longer gradually. Okay, so that's why the amorphous solids, okay, the AM or AS for short, amorphous solids will have not sharp melting points, okay, so they will start melting at, for example, different temperature and fully melt at different temperature. Okay, so no sharp melting point in case of amorphous solids and sharp melting point in case of crystalline solids. Okay, so we say that these crystalline solids have repetitive structure, whereas we say that amorphous solids do not have such a structure. How we so say that? Okay, we say that because of X-ray diffraction we do with these materials. X-ray diffraction. Okay, so we place a solid amorphous or crystalline as a grating. Okay, as a grating, and we will see the diffraction pattern, and we will use X-ray for these studies. Okay, and we see that in case of crystalline, we see that in case of crystalline materials we get particular and limited peaks. So these peaks, for example, like this, okay, at different positions. Okay, for example, we get limited peaks. Okay, so these peaks are characteristics of a solid. So if I look at this peak, I can say that this is NaCl, for example. Okay, if we see the different peaks, then I can say that it is not NaCl but different material. Okay, so with X-ray diffraction we can see the internal structure, and we can also recognize the material of which the solid is made. Okay, so these X-ray diffraction give limited or particular peaks in case of crystalline solid, whereas for amorphous solids, or AS in short, there is number of peaks, a lot of peaks are there. Okay, with the same material, if you do different samples, you will get different peaks. Okay, so due to these in crystalline solid, it is easy to do structural analysis, but it is very difficult in case of amorphous solids. Okay, difficult in case of amorphous solids. Okay, the easy structure analysis is possible due to the regular arrangement and order of the crystalline solids, but which lacks in amorphous solids. Okay, so in crystalline solids we have a repetitive pattern of arrangement, a regular repeated pattern of atoms and molecules exist in case of crystalline solids. So in other words, the condition in a crystal are this way. The environment of a particular atom in a crystal has a certain arrangement. Okay, and if you look at some same kind of atom at another place farther along, you will find one whose surroundings are exactly the same. Okay, if you pick an atom farther along by the same distance, you will find the conditions exactly the same. Okay, so we say that pattern is repeated over and over again, and of course into 3 dimensions. Okay, so for example, if we take this crystal, okay, I cannot make infinite crystal because of the limitations of the pages. Okay, the space available to me. Okay, so every intersection is an atom. So this is an atom. Let me make big atoms. These are atoms. These are atoms. Okay. So environment of each atom is same. For example, this atom, if we see, okay, if we see this atom, then it is surrounded by, it is attached to 4 atoms. One is this, second, third and fourth. Okay, so these are all atoms. They have same surroundings. Okay, so if you wait a minute. So if you look, for example, at atom A, which is this atom, okay, it has in its surroundings, for example, 3 above, 3 below and 2 on sides. If we go some distance, for example in this direction, then this atom B is also having the same environment about it. Okay, the surrounding of atom A and atom B in the same crystal is same. Okay, they are exactly same, and this is happening in 3 dimensions. Okay, so this type of thing we called a crystalline solid. So this is a example of crystalline solid. Crystalline solid. So these pattern of atoms in a crystal are found by the X-ray diffraction. Okay, we do this experimentally, and it has been the X-ray diffraction pattern, X-ray diffraction. Okay, it has been worked out for most simple crystals and also to some fairly complex crystals. Okay, so it is done for a lot of crystals, and we found the arrangement of these crystals using this technique of X-ray diffraction. So this internal pattern of crystal shows up in several way in real world. Okay, the first is the binding strength of atoms in certain direction is usually stronger than in other direction. Okay, as we talked above. Okay, in crystalline solids, the binding strength of atom in certain direction can be stronger than in other directions. So this means that there are certain planes through the crystal where it is more easily to break the crystal, okay, as compared to the other planes. Okay, so for example, if this is less bond length, okay, and this is more bond length in this direction, because this is length, the smaller bond length. Okay, this is A, this is B, and if A is smaller than B, the bond length A and B, then it means that this is a stronger bond, because the atoms are close to each other, and there are atoms are farther apart, so it is easy to cut a crystal through this plane. Okay, it is easy to cut the crystal through these planes. Okay, and relatively more difficult to cut through these planes. Okay, so these planes are called cleavage planes. Along which we can easily cut a crystal. These are called cleavage planes. So if you try to crack a crystal with a knife, okay, it will often split along such a plane. Okay, we can cut through a crystal in this plane also, but it will require more force as compared to this direction. Okay, so these through which we can cut a crystal are called cleavage planes. Okay, so that's how the internal structure of the crystal shows up into the real world. Okay, and the second way it shows into the real world is the internal structure often appears at the surface. Okay, so the internal structure, for example, this is a square lattice, then the crystal made up out of these structure will have real square surface faces of a whole crystal. Okay, and the internal structure often appears at the surface because of way the crystal was formed. So for example, imagine a crystal being deposited out of solution. Okay, so in solution, that is in liquid form, the atoms are floating around in solution and finally they are settling down. So these are the atoms in a solution. Okay, so the solution is starting to crystallize. Okay, so these atoms one by one will come into an ordered places like this. Okay, so they will finally settling down. Okay, so when they find a position with lowest energy. Okay, so here you can appreciate that there will be certain directions in which it will grow at different speeds. For example, if this is a shorter, for example here, this is because short bond, so these are strongly connected, so they will, okay, so in these direction they may grow at large speed, okay, as compared to this direction, and thereby they will grow into some kind of geometrical shape because there are more uh, large speed in this as compared to small speed in this direction. So it will, the crystal will look like a rectangle, okay, or a cuboid when grown into a full crystal. Okay, and because of such effects, the outside surface of many crystals show some of the character of internal geometry of atoms. For example, if we take the example of this, the shape of quartz crystal, shape of quartz crystal, quartz crystal. Okay, shape of the quartz crystal. Its internal pattern is the hexagonal pattern. Hexagonal pattern. Okay, if you look closely at such a crystal, you will notice that the outside does not make a very good hexagon because the sides are not equal. So some of the sides are like this big, some of sides are this big, like this. Okay, is it a hexagon? No, this is the third side, fourth side, fifth side and sixth side. Okay, so the sides are not be of equal length. Okay, they are in fact often very unequal, but in one respect it is a very good hexagon. Okay, the quartz crystal, in one respect it is a very good hexagon because all the angles are 120-degree. Okay, here I was unable to make them 120-degree, but when you see a real crystal of quartz, you will see that the angles are exactly 120 degree between the faces. Okay, so we can say that the size, we can say that why the size were different of different sides. Okay, we can say that size of a particular face is the different due to the accident of the growth. It means that when the crystal uh, was preparing in some earth or somewhere, one side is more, for example, faced more pressure, for example, than the other, so that's why it is shorter than the other. Okay, so but the angles are all 120 degree, and these angles are true representation of the internal geometry of crystal. Okay, so every crystal of quartz have different shapes, even though the angle between the corresponding faces are always the same, that is 120 degree. Okay, the second example is the internal geometry of sodium chloride. Okay, okay, it also appears on the external shape. Okay, the internal geometry of NaCl is cubic. Okay, and if you see the crystals of common salt, you will see that they are not perfect cubes, but you will find that faces are exactly at right angle to each other. So faces are at perpendicular to each other, are perpendicular to each other. Okay, so this is the properties of crystals. So we see that crystalline solids have ordering and repetition between the crystals. Okay, the crystalline solids exhibit a high degree of order, with atoms forming repeating patterns that extend throughout the material. Okay, they have cleavage and symmetry. The crystalline solids possesses the cleavage planes resulting from the arrangement of atoms. Okay, so crystal display various degrees of symmetry based on their crystal. Okay, and they will exhibit unique optical behavior due to the order arrangement. Okay, such as bifringes, crystallographic colors. Okay, however, in amorphous solids there is a lack of order. Okay, the repeating arrangement is not there of the atoms and molecules of the amorphous solids. Okay, so this give them the glassy appearance. Okay, super cool, also called the super cool liquids. Okay, so there is isotropic properties, whereas in case of crystals there is anisotropic properties. Okay, their physical the amorphous solids physical properties are uniform in all direction, unlike the crystalline solids. Okay, amorphous solids have a glass transition temperature. Okay, they have glass transition temperature, so when they transition from the rigid to more flexible state, they melt gradually, not sharply. Okay, so example of crystalline solids we saw NaCl. Okay, another example is of the crystalline solid is diamond. Okay, diamond is a crystalline solid. NaCl and metals, okay, these are crystalline solids. Okay, for example, copper, gold, etc. Okay, so these are called metallic crystals. Okay, and amorphous solids, glass, rubber, these are the example of amorphous solids. And certain plastics. Okay, these are the amorphous solids. There are also amorphous metals. Okay, okay, and there are some solids like B2O2 which exist in both states, the crystalline as well as amorphous. Okay, so that's it about this lecture. So we saw that crystalline solids are characterized by their ordered atomic arrangements, distinct properties, and well-defined shapes. In contrast, amorphous solids display a lack of long range order, isotropic properties, and a glass transition temperature. Both these type of solids play crucial roles in material science, with applications ranging from electronics to architecture. So thank you for joining me, and this will be the end. Okay, thank you.